Have you ever watched a ripple spread across a pond, or felt the vibrations of a sound wave travel through the air to your ear? Perhaps you have seen sunlight split into a rainbow by a prism. These everyday experiences illustrate a profound concept that scientists pondered for centuries before the advent of quantum physics, shaping our fundamental understanding of reality. In the macroscopic view, a wave was fundamentally understood as a continuous disturbance that propagates through a medium, transferring energy without transferring matter itself. It was seen as an extended phenomenon, characterized by measurable properties like amplitude, wavelength, and frequency, all of which were observable and predictable. This classical perspective provided a clear, intuitive model for how energy moves through the universe. The core mechanism of classical waves relies on the idea of a vibrating or oscillating source causing a disturbance that travels through interconnected particles or fields. For instance, sound waves requiring air molecules to bump into each other in a chain reaction, creating regions of compression and rarefaction. Ocean waves, similarly, need water to move up and down as energy passes through it. Even light, while not needing a physical medium in the same way as sound or water, was understood as an oscillation of electromagnetic fields. Scientists meticulously described these behaviors using sophisticated classical wave equations, predicting precisely how waves would reflect it off surfaces, refract when entering new mediums, diffract around obstacles, and constructively or destructively interfere with one another, creating intricate and predictable patterns. To observe and quantify these wave properties, early scientists meticulously designed ingenious experiments. Think of the simple act of dropping a stone into water to see concentric ripples expanding outwards, demonstrating propagation and wavelength. For sound, striking a tuning fork and noticing how its pitch relates to frequency provided direct evidence. A pivotal example for light was Thomas Young's famous double-slit experiment in the early 1800s. This experiment clearly demonstrated interference patterns, conclusively showing light behaving as a wave. This practical understanding was not just academic. It allowed engineers to design advanced optics for powerful telescopes and microscopes, and to develop groundbreaking technologies like radio communication, all based on the reliable, continuous wave nature of these phenomena. An interesting and powerful detail in the classical wave model is the concept of a wavefront. Imagine a hypothetical surface connecting all points of a wave that are currently in the same phase. For example, the crest of an ocean wave or the peak of an electromagnetic oscillation. This idea, which is central to Huygens' principle, was instrumental in explaining complex phenomena like diffraction, where waves appear to bend around obstacles or spread out after passing through an opening. Another key aspect was the assumption of continuous energy transfer. A classical wave could theoretically carry any arbitrary amount of energy, not just discrete, quantized packets, a notion that would later be dramatically revised by quantum theory. This robust macroscopic view of waves provided an incredibly powerful and successful framework for understanding and manipulating the world around us for centuries. It beautifully explained everything from the vibrant colors of a rainbow to the fundamental operation of a radio, establishing a highly intuitive and predictive picture of how energy moved through the universe. This classical understanding was not a failure. Rather, its immense success laid the essential groundwork and set the stage for the revolutionary insights of quantum mechanics, which would ultimately challenge and expand these very foundations at the microscopic scale.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.